Hello there, and welcome. I am so glad you found your way here tonight. Whether you stumbled across this by accident or you have been here before, it does not matter. What matters is that you are here now, and that is enough. Maybe it has been a long day. Maybe your mind is still quietly rehearsing conversations that already ended, or running through tomorrow's list before tomorrow has even begun. That is all right. That is what minds do. But tonight, you do not have to follow yours wherever it wants to go. You can simply let it slow down, the way a river slows when it finally reaches flat, open ground. Tonight, we are going to drift through one of the most ancient and beautiful processes in the entire universe, the way stars die. Not with fear, not with urgency, but with the quiet wonder of someone lying on their back in an open field, watching light cross a very dark sky. Stars are not permanent. They are born, they burn, and they end. And in their ending, they give away everything they ever were. The iron in your blood, the calcium in your bones, the oxygen in the air you are breathing right now. All of it came from stars that were already gone before our sun was born. We are made of old light. We are resting on a planet built from stellar ash. There is nothing to figure out tonight. Nothing to solve. You have nothing to do tonight but rest. If these quiet journeys help you unwind at the end of a long day, consider subscribing. One sleepy soul at a time. Now, let us begin. Every star you can see with your naked eye will one day die. On a clear night, far from city lights, a person with good eyes might count 2,000 stars overhead. Each one is a sun. Each one is burning, fusing hydrogen into helium deep in its core, producing the light and heat that keeps it inflated against its own gravity. It looks permanent, it looks fixed, but every single one of those lights is living on borrowed time. The sun itself has been burning for about 4.5 billion years, and it has roughly the same amount of time left. When we look up at a clear night sky, we are looking at a graveyard in slow motion, full of stars that do not yet know they are dying, arranged in their familiar patterns, quietly counting down. Even now, as you drift, the light reaching your eyes left those stars thousands of years ago, and they have already moved on. A star's death is decided the moment it is born. The most important thing about any star, how long it will live, how it will end, what it will leave behind, is set by a single number, its mass. A small, lightweight star like a red dwarf will burn so slowly and carefully that it could live for trillions of years. Our sun, a mid-sized yellow star, will live for about 10 billion years total. A massive blue supergiant, many times heavier than our sun, burns so furiously that it exhausts itself in just a few million years. Think of it like fire in a fireplace. A small, tight bundle of dry wood burns slowly and steadily through the night. A pile of paper catches fast, blazes bright, and is gone in minutes. The more fuel you give a fire, the faster it burns. And in the universe, mass is everything. The largest stars live the shortest lives, burning quiet and bright, and briefly against the ancient dark. Our own sun is middle-aged, unremarkable, and perfectly placed. Astronomers classify it as a G-type main sequence star, which sounds technical, but what it means is simple. It is a calm, average-sized star doing average-sized things. It is not the brightest star in the galaxy. It is not the largest. It is not the most energetic. Of the roughly 200 billion stars in the Milky Way, our sun sits somewhere in the quiet middle of almost every measurement. And that ordinariness is, in a strange way, what makes life on Earth possible. Violent, fast-burning stars do not give planets time to cool, settle, and grow complex chemistry. Our sun burns at just the right pace, slowly enough for 4 billion years of evolution to unfold, calmly enough for us to be here tonight, lying still, breathing slowly in the dark. There is something restful about being ordinary, something ancient and safe. Stars spend most of their lives doing almost nothing dramatic. This surprises people. We tend to imagine space as a place of constant explosions and collisions, and some parts of it are. But a star in its main sequence phase, which is most of its life, is in a state of deep, stable balance. Gravity is always trying to pull the star inward, toward its own center. Nuclear fusion is always pushing outward, radiating energy in every direction. These two forces meet exactly, holding the star at a steady size and temperature for billions of years. Astronomers call this equilibrium. It is, in a sense, a very long rest. The star is not straining. It is not struggling. It is simply burning at the rate it was always going to burn, balanced between collapse and expansion, doing the same thing every second of every year across geological time. A star at rest is a star in perfect, patient balance, and balance, in the end, is all any of us are looking for. When a star like our Sun finally runs low on hydrogen, something quiet and slow begins to shift. For billions of years, hydrogen fusion in the core keeps everything stable. But hydrogen is not infinite. As the core begins to run out, fusion slows, and the outward pressure that was holding the star up starts to weaken. Gravity, which never stops pulling, takes its opportunity. The core begins to contract. It squeezes tighter, and as it squeezes, it heats up. That new heat is enough to ignite hydrogen fusion in the layers just outside the core, a shell of burning gas surrounding a shrinking center. And the energy from that shell begins to push the outer layers of the star outward. Very, very slowly, the star begins to swell. It takes millions of years, but it begins. Something is always beginning its slow unraveling, long before we notice the first signs. As a sun-like star swells, it becomes what astronomers call a red giant. The outer layers expand so much that the star's surface moves farther from the core, and that distance allows it to cool slightly. Cooler surfaces glow red or orange instead of yellow or white, and so the star grows enormous and turns red, a red giant, sometimes hundreds of times the diameter it once had. For our own sun, this expansion will eventually reach far enough to swallow Mercury, then Venus, and possibly the Earth itself. The Earth's oceans will have long since boiled away before that moment arrives. The atmosphere will have stripped off, the surface will be bare and burning, and the sun will keep expanding, slowly and indifferently, the way a wave spreads across still water, not angry, not deliberate, just following the physics it was always going to follow. We drift through our lives the way planets drift through their orbits, quietly, slowly, following the pull of something enormous we cannot see. Red giant stars lose mass through powerful stellar winds. As a star, in its red giant phase grows large, and its outer layers become more loosely bound, the radiation pressure from the core starts to push material outward into space. Not in a sudden explosion, but in a constant, slow exhalation. A stellar wind that carries gas and dust away from the star over millions of years. Our own sun, even now, has a solar wind. It blows past Earth every second of every day, streaming charged particles out through the solar system. But in its red giant phase, that wind will grow thousands of times stronger. The star will slowly breathe itself away, shedding its outer layers into the space around it, leaving a trail of gas that will glow in the dark for thousands of years, lit from within by the shrinking star at its center. Astronomers call these glowing clouds planetary nebulae, and they are among the most quietly beautiful structures in the galaxy. Tonight, while you breathe slowly, somewhere in the galaxy, a star is breathing its last, softly exhaling itself into the dark. Planetary nebulae have nothing to do with planets. The name is a historical accident, a case of mistaken identity from the early days of astronomy. When astronomers in the 18th century first observed these glowing circular clouds through their early telescopes, the fuzzy round shapes reminded them of planets, specifically of the disc-like appearance of Uranus, which had just been discovered. So they called them planetary nebulae, and the name stuck, even after everyone understood they had nothing to do with planets at all. They are actually the expelled outer shells of dying stars, clouds of gas lit up by the ultraviolet radiation pouring from the hot stellar remnant at their centers. They come in rings, in hourglasses, in lopsided puffs of colored light, in shapes that look almost like eyes, or flowers, or smoke rings, drifting slowly outward through the dark. A name given in error, and yet it holds. Some of the most beautiful things in the universe arrived by accident. At the center of every planetary nebula sits a white dwarf. After a sun-like star has expelled its outer layers, what remains is the naked core, a dense, hot, glowing remnant about the size of Earth, but with roughly half the mass of the original star. This object is a white dwarf, and it is one of the strangest, most quiet endpoints in stellar physics. It no longer generates energy through fusion. It has no fuel left. It simply glows from the heat it accumulated over billions of years, a remnant of an enormous fire, cooling down, incredibly slowly, over trillions of years. A white dwarf does not burn, it rests. It holds the memory of the star it once was, in its hot, compressed body, and slowly, patiently, releases that heat into the surrounding dark. Even after the burning ends, warmth lingers. It fades slowly, like the last light in a room after the candle is gone. White dwarfs are made of material denser than anything on Earth. When you compress roughly half the mass of our sun into a sphere the size of our planet, the matter inside behaves in ways that have no parallel in everyday experience. The electrons in the atoms are squeezed so tightly together that they push back against gravity through a quantum mechanical effect called electron degeneracy pressure. The atoms are not fused, the electrons are not captured, but they are packed so closely that they resist further compression through pure quantum stubbornness, a property of matter at the very small scale that says, in essence, two electrons cannot occupy the same state in the same place. That resistance is what holds the white dwarf up, not heat, not fusion, just the fundamental rules of quantum mechanics, enforced at stellar scale. There is a kind of quiet resistance in the smallest things, a stubbornness built into the fabric of matter itself. A white dwarf can, under certain conditions, explode. A white dwarf sitting quietly in space, slowly cooling over billions of years, seems like the very definition of a peaceful end. But if it has a companion star, another star orbiting close enough, it can pull material from that companion onto its own surface. Slowly, over time, it accumulates mass. Hydrogen and helium drift down onto the white dwarf's surface, and if the conditions are right, they can ignite in a sudden flash of nuclear burning, called a nova. The white dwarf survives a nova. It keeps accumulating. But if it keeps pulling mass until it reaches a critical threshold known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, something more final happens. The entire white dwarf detonates in a thermonuclear explosion so bright it can outshine an entire galaxy. This is a Type 1 supernova, and it is one of the most violent and quiet endings in the universe. As you rest tonight, somewhere in the observable universe, a white dwarf just crossed its limit, silently, without warning. Not all stars end as white dwarfs. For stars significantly more massive than our Sun, typically those with more than 8 times its mass, the story ends differently and more violently. These stars burn through their hydrogen rapidly. Then they burn helium, then carbon, then oxygen, then neon, then silicon. Each fuel source burns faster than the last, and the star builds up layers of progressively heavier elements in its core, like the rings of a tree laid down in increasing density. Eventually, the core fills with iron, and iron is where the story stops. Unlike lighter elements, iron does not release energy when it fuses. It absorbs it, and so the fusion engine that has powered the star for millions of years, The engine that held up billions of miles of gas against the pull of gravity simply stops. The support vanishes, and gravity, patient and relentless, wins. Gravity never stops pulling. It waits at the edges of every life, biding its time in the quiet dark. When a massive star's iron core collapses, it happens almost instantly. The outer layers of the star, which have been held up by the energy from the core for millions of years, suddenly lose their support. They fall inward at a quarter of the speed of light. The core, now compressed beyond anything a white dwarf could survive, crushes into a sphere just a few miles across, made entirely of neutrons packed together at nuclear density. The infalling outer layers slam into this newly formed neutron star and bounce, sending a shockwave rippling back outward through the star at incredible speed. That shockwave tears the star apart. In a fraction of a second, a star many times the mass of our Sun destroys itself in an explosion called a core collapse supernova. For a few weeks, that single explosion can outshine the entire galaxy it lives in. Something that took millions of years to build can end in less than a second. The universe is patient until it isn't. Supernovae are how the universe makes and spreads heavy elements. Before the first stars formed, the universe contained almost nothing but hydrogen and helium, the two simplest, lightest elements on the periodic table. Everything heavier than that was made inside stars, through billions of years of nuclear fusion. Carbon, nitrogen, oxygen, sulfur, calcium, iron, all forged in stellar cores under conditions of unimaginable heat and pressure. But those elements are no good to anyone if they stay locked inside a star. It is the supernova that sets them free. The explosion blasts the star's outer layers outward at thousands of miles per second, seeding the surrounding space with all the elements the star spent its life creating. Those elements drift through the galaxy for millions of years, eventually becoming part of new clouds, new stars, new planets, and new life. Every element that makes you is a gift from a star that ended its life to give it away. You are ancient and freely given. The light from a supernova can take thousands of years to reach us. We do not see supernovae in real time. When a massive star explodes somewhere in a distant galaxy, the light from that explosion travels toward us at the speed of light, roughly 186,000 miles per second. But the distances involved are so enormous that by the time that light reaches our eyes, or our telescopes, the explosion itself happened long before any human civilization existed. When astronomers observe a supernova today, in a galaxy 50 million light-years away, they are watching an event that occurred 50 million years ago, before mammals were even the dominant life form on Earth. We are looking into the past every time we look at the sky. The universe is a time machine, and space is its long, slow corridor. To look up is to look back. Every light in the sky is a quiet message from a moment already gone. A supernova visible to the naked eye is a rare and ancient gift. In recorded human history, only a handful of supernovae have blazed brightly enough to be seen without a telescope. In 1054, astronomers in China and the Middle East recorded a new star appearing in the sky, so bright it was visible in daylight for weeks. What they saw was the death of a massive star about 6,500 light-years away. That explosion had actually happened 6,500 years before they saw it, during the late Stone Age. What it left behind was a cloud of glowing gas we now call the Crab Nebula, and at its center, a spinning neutron star. The people who watched that star appear in the daytime sky had no way of knowing they were seeing the death of a sun, or that what it left behind would still be glowing 1,000 years later, slowly expanding into the dark. Ancient watchers looked up in wonder at a light they could not name. Some things are still worth watching, even when we do not understand them. Quietly, the cosmos moves around you. Neutron stars are among the densest objects that can exist. After the supernova shockwave has passed, What remains at the center is a neutron star, and its properties strain every intuition we have about matter. A neutron star typically contains between 1 and 2 solar masses of material, compressed into a sphere just 12 to 15 miles in diameter. To put that in terms that have some human texture to them, if you took the entire mass of our sun, a ball of gas 100 times the diameter of Earth, and squeezed it into a city roughly the size of Chicago, you would have a neutron star. The density of its interior is comparable to the density of an atomic nucleus. A single teaspoon of neutron star material would weigh approximately 1 billion tons on Earth's surface. And somehow, this object holds together, held in place by the same quantum stubbornness that supports the white dwarf, scaled to an extreme, barely describable in human language. Something impossibly dense can still be impossibly quiet. The most compressed things often make the least sound. Neutron stars spin rapidly, often hundreds of times per second. When a massive star collapses, its core retains almost all of the angular momentum of the original star, but in a much smaller body. This is the same physics that makes a spinning ice skater pull in their arms to spin faster. Conservation of angular momentum. The result is that some newly formed neutron stars rotate dozens or even hundreds of times per second. These rotating neutron stars often emit beams of radio waves or X-rays from their magnetic poles, and as those beams sweep around like lighthouse beacons, they can be detected from Earth as precisely timed pulses. We call them pulsars. Some pulsars are so precise in their timing that they rival the accuracy of atomic clocks. Millisecond pulsars have been used to test some of the most fundamental equations in physics, spinning through the dark with a mechanical regularity that is almost surreal. Something at the edge of destruction can still be extraordinarily precise. The universe keeps its own careful time, even in the ruins. The fastest spinning pulsars challenge the limits of what matter can withstand. Millisecond pulsars, which are neutron stars that have been spun up to extreme rotation speeds by pulling material from a companion star, rotate up to 700 times per second. At that speed, the equator of a neutron star is moving at a significant fraction of the speed of light, millions of miles per hour. If a neutron star were to spin just a little faster, the centrifugal force at its equator would overcome the immense gravity holding it together, and it would begin to shed mass, or even tear itself apart. There is a theoretical maximum rotation rate for neutron stars, and some of the ones we have observed are approaching it. They are spinning at the edge of their own dissolution, balanced between survival and disintegration, every second of every day, out in the quiet dark. Even in perfect stillness from a distance, the most extreme things are always on the edge of something. Rest, for now, is enough. Some neutron stars have magnetic fields 1 trillion times stronger than Earth's. Ordinary neutron stars already have magnetic fields that dwarf anything in our solar system. But a small subset of neutron stars, called magnetars, have magnetic fields that exceed even those by factors of 1,000 or more. A magnetar's field is so powerful that, at a distance of roughly 600,000 miles, the same distance as from the Earth to the Moon, it would disrupt the chemistry of every molecule in a human body. At closer ranges, it would rearrange the atoms themselves. These objects do not persist quietly in space. They occasionally release enormous bursts of X-ray and gamma-ray energy in events called starquakes, when the rigid crust of the neutron star cracks under the strain of its own magnetic field. In 2004, a magnetar 50,000 light-years away released a burst of energy in 1/10 of a second that exceeded everything our sun will radiate in 100,000 years. The quietest places in the universe sometimes hold the most extraordinary tension. Even silence can have an interior. When enough mass collapses, not even light can escape. There is a threshold beyond neutron stars, a point at which the mass of the collapsing core is so great that even neutron degeneracy pressure cannot hold it up. When that happens, nothing can stop the collapse. The core continues inward, past the neutron star stage, past any known stable state, and into a singularity, a point of infinite density where the known laws of physics stop describing what happens. Surrounding that singularity is a region of space called the event horizon, the boundary beyond which nothing, not matter, not radiation, not light itself, can escape. We call this a black hole. A black hole does not suck things in like a vacuum cleaner. It simply warps the space around it so severely that inside a certain radius, all paths through space, including the path light tries to take, curve inward. There is no way out, because there is no direction that leads anywhere but in. The darkest places in the universe are not empty. They are simply regions where the path outward no longer exists. Black holes left behind by supernovae are called stellar mass black holes. Not all black holes are the enormous, terrifying objects at the centers of galaxies. The black holes formed by the collapse of massive stars are relatively modest, typically between 5 and several dozen times the mass of our Sun. They sit quietly in the dark, invisible to telescopes that detect light, discoverable only by their effects on surrounding matter and space. A stellar mass black hole alone, in the empty space between stars, is genuinely difficult to detect. It emits nothing. It produces no light. It simply warps the space around it, slowly and patiently, for billions of years. Some stellar mass black holes have companion stars, and by watching the way material pulled from those companions spirals inward and heats up, astronomers can map the black hole's presence. But in isolation, they are among the most hidden things in the known universe, ancient, dark, and still. There is something deeply restful about things that ask nothing of you. The universe holds many quiet, hidden places. The first black hole ever confirmed was found through the motion of a companion star. In the 1960s and 1970s, astronomers studying X-ray sources in the sky noticed something unusual in the constellation Cygnus. A powerful source of X-rays called Cygnus X1 was fluctuating rapidly, which suggested the object producing it was small. When they traced the X-rays back to a visible star in that region, they found a massive blue supergiant orbiting something they could not see. By measuring the motion of the visible star, they calculated that whatever it was orbiting had a mass of at least 10 times our Sun, far too heavy to be a neutron star or white dwarf. There was only one candidate. Cygnus X1 became the first black hole candidate accepted by the scientific community. It sits about 6,000 light-years away, close in cosmic terms, a dark companion to a bright star, circling quietly in the slow dark of the Orion Arm. Some things reveal themselves only through what they move. What is hidden shapes what we can see. Black holes do not last forever. They very, very slowly evaporate. In 1974, the physicist Stephen Hawking made one of the most counterintuitive predictions in modern physics. Black holes are not truly black. They slowly emit a faint form of radiation, now called Hawking radiation, through a quantum mechanical process at their event horizons. In a vacuum, pairs of virtual particles are constantly appearing and disappearing. Near a black hole's event horizon, one particle from a pair can fall in, while the other escapes, carrying energy away from the black hole. Over astronomical timescales, far, far longer than the current age of the universe, this process gradually reduces the black hole's mass. The smaller the black hole, the faster it evaporates. Very small black holes would disappear in a flash of radiation, but a stellar mass black hole would take something on the order of 10 to the 67th power years to evaporate completely, a number so large it dissolves into meaninglessness. Still, it ends. Even the darkest, most permanent-seeming things carry within them the slow logic of an ending. Even now, as you drift, when two neutron stars spiral together, they create gold. For decades, physicists debated where the heaviest elements in the universe actually come from. Iron and everything below it is made in stellar cores, but elements heavier than iron, gold, platinum, uranium, iodine, require conditions of extreme neutron density to form, conditions rare even in supernovae. The answer, confirmed in 2017, came from a gravitational wave detection event. Two neutron stars, each weighing more than the Sun, orbited each other over millions of years, slowly radiating energy as gravitational waves, spiraling inward at a pace too slow to perceive. Then, in an instant, they merged. A kilonova explosion that released more energy in its brief blaze than the Sun will emit in its entire 10 billion-year life. The explosion was rich in heavy elements. Astronomers detected gold and platinum in the expanding cloud of debris. The gold in your jewelry was made in a collision like this one, somewhere in the ancient universe, long before our Sun existed. The gold that catches light on your skin was forged in a collision between two dead stars, flung across the ancient dark to reach you. Gravitational waves are ripples in the fabric of space itself. The collision of two neutron stars, or two black holes, does not just release light and matter, it also sends ripples through the geometry of space-time, spreading outward from the merger at the speed of light. These are gravitational waves, first predicted by Albert Einstein in 1916, as a consequence of his general theory of relativity. For over a century, they remained theoretical, too faint, too subtle, to detect with any technology we had. Then, in September 2015, the LIGO detectors in Louisiana and Washington state detected the gravitational waves from two black holes merging 1.3 billion light-years away. The signal lasted for less than a second. The distortion it caused in the detectors was smaller than 1/10,000th the diameter of a proton. And yet we caught it. We felt a ripple from a collision that happened before complex life existed on Earth, washing through us, through the planet, through everything, like a faint, silent wave. The universe moves through us, whether we feel it or not. We are always inside something vast and slow and gentle. The Milky Way's central black hole is 4 million times the mass of the Sun. At the center of our galaxy, roughly 26,000 light-years away, sits a supermassive black hole called Sagittarius A star. It is not the largest supermassive black hole known. It is not even particularly active by galactic standards. But it is ours, and its scale is difficult to hold in the mind. 4 million solar masses, compressed into a region smaller than the distance between our Sun and its nearest neighboring star. We cannot see it directly. It is hidden behind dense clouds of gas and dust. But we can see the stars orbiting it, circling around the black hole's invisible center at hundreds of miles per second, tracing tight, elliptical paths that take only a few years to complete. By watching those orbits with infrared telescopes for decades, astronomers have mapped the black hole's presence with extraordinary precision. It sits at the center of everything we call home, quiet and enormous, in the dark. Quietly, the cosmos moves around you. Even now, as you rest, you are slowly orbiting a darkness 4 million times the weight of the Sun. Most galaxies have supermassive black holes at their centers. This is one of the more quietly profound discoveries of the last few decades. The realization that supermassive black holes are not rare or exotic features of unusual galaxies. They are standard equipment. Almost every large galaxy that astronomers have looked at closely appears to have a supermassive black hole at its center, ranging from millions to billions of solar masses. How they form is still an open question. They may have grown from smaller black holes merging over billions of years. They may have formed from the direct collapse of enormous gas clouds in the early universe. They may have grown in tandem with their host galaxies, feeding on infalling gas and dust, while their galaxies built up around them. In a strange way, you and the supermassive black hole at the center of our galaxy grew up together, both part of the same slow, patient, ancient story of the Milky Way. Everything that exists is part of the same old story, told slowly, patiently, across a scale of time that asks nothing of us but to rest inside it. The death of massive stars shaped the chemical history of the universe. Step back far enough, and the death of stars is not a tragedy. It is an engineering process. The universe started out simple: hydrogen, helium, and trace amounts of lithium. Everything more complex than that was absent from the original inventory. It was stellar evolution, billions of years of stars forming, burning, exploding, and seeding the galaxy with new elements that gradually enriched the cosmos with the chemistry of complexity. Each generation of stars was born slightly richer in heavy elements than the last, because each generation inherited the ashes of the one before it. Our Sun is a third-generation star. It formed from material that had already passed through at least 2 previous cycles of stellar birth and death. We live on a planet made of third-generation stardust, breathing air assembled by stars we will never see, carrying iron forged in hearts that stopped beating billions of years before we arrived. We are, all of us, late arrivals in a universe that was already ancient. Built from what came before, quietly and completely, some of the most beautiful objects in the universe are nothing but the lingering remains of dead stars. Nebulae, glowing clouds of gas and dust, come in many forms, and many of the most visually rich ones are the remnants of stellar deaths. The Crab Nebula is a supernova remnant. The Ring Nebula is a planetary nebula, the expelled shell of a dying sun-like star. The Helix Nebula, sometimes called the Eye of God, is another planetary nebula, 12 light-years across, glowing in delicate rings of teal and red. These objects are not permanent. They expand and thin over thousands of years, and eventually, the gas disperses, cools, and becomes part of the background medium of the galaxy, available to be folded into new stars and new worlds. The beauty of a nebula is the beauty of an ending that has not yet finished, still glowing, still expanding, still giving. Beauty that is ending is still beauty. The glow does not stop being warm simply because it is fading. The universe is in the business of making stars, and has been for billions of years. The cycle of stellar birth and death is not a one-time event. It is ongoing. Gas collapses under gravity to form new stars. Those stars live and eventually die, returning enriched material to the galaxy. That material cools, condenses, and eventually becomes the raw material for the next generation of stars. This cycle has been running for the roughly 13.8 billion year age of the universe, and it is still running now. The star-forming regions of our galaxy, vast clouds of cold gas and dust, like the Orion Molecular Cloud, are actively producing new stars at this moment. Somewhere in those clouds, right now, a protostar is gathering mass, heating its core, building toward the moment it ignites. The universe has been making suns for nearly all of its existence, quietly and continuously, the way a river makes and unmakes its bed. Something is always beginning somewhere, quietly, in the dark between the stars, without announcement, without anyone watching. Rest here for a moment. There is more to come. The universe began making stars before it made anything else worth naming. In the first few 100 million years after the Big Bang, the cosmos was dark, not metaphorically, but literally. There were no stars, no galaxies, no light sources of any kind. Just an expanding fog of hydrogen and helium, slowly cooling, slowly clumping under gravity. Astronomers call this period the Cosmic Dark Ages, and it lasted for somewhere between 100 and 500 million years. Then, in pockets of slightly denser gas, scattered across the dark, gravity pulled enough material together for the first stars to ignite. These first stars, called Population 3 stars, were enormous, possibly hundreds of times the mass of our Sun. They lived briefly, burned violently, and died in supernovae that scattered the first heavy elements across the infant universe. We have never directly observed one. They are too distant, too ancient, their light too faint. But their deaths are written in everything that came after. The oldest things leave no direct trace. They are present only in what they made possible. The first stars in the universe were almost certainly blue. Color in a star is a direct readout of surface temperature. The hottest stars burn blue-white. Slightly cooler stars burn white or yellow. Cooler still, and they glow orange or red. The very first stars, being massive and burning at extreme temperatures, would have blazed blue-white against the absolute darkness of the early universe. There was nothing to compare them to. No other light source existed anywhere. A universe that had been completely dark for hundreds of millions of years suddenly, in one region after another, began to ignite. Blue points of brilliant light appearing in a deep, total dark. Astronomers believe this moment, called reionization, was when the universe became transparent again, as the radiation from those first stars stripped the electrons from the surrounding hydrogen fog and allowed light to travel freely for the first time since the early moments after the Big Bang. Something patient and dark suddenly bloomed with light. The universe has always known how to begin again, slowly and without ceremony. Stars form inside cold, dark molecular clouds. Look at a photograph of the Milky Way, and you will notice dark patches, regions where fewer stars seem to be visible. Those dark patches are not empty. They are cold molecular clouds, drifts of hydrogen and dust so dense that they block the light of the stars behind them. These are stellar nurseries, the places where new stars are born. Inside these clouds, over millions of years, slight variations in density become amplified by gravity. A denser pocket pulls more material toward it. That material heats up as it falls inward. If enough mass accumulates, the temperature and pressure at the center rise high enough to ignite hydrogen fusion, and a star is born. The cloud that surrounded it, heated and pushed by the new star's radiation, slowly disperses. The star emerges into the open, newly formed, burning quietly, beginning its long and steady life. Every star was once cold and dark and formless. The light came later, from the slow patience of gravity doing its work. As you rest tonight, new stars are forming inside clouds we can barely see. Even now, in the Orion Molecular Cloud, one of the closest star-forming regions to our solar system, roughly 1,350 light-years away, gas is condensing, protostars are gathering mass, and the slow process of stellar ignition is underway. These are not rare events happening in distant corners of the universe. They are happening in our own cosmic neighborhood, right now, tonight, while you lie still and breathe slowly. The Milky Way forms somewhere between 1 and 3 new stars per year, on average. A quiet, steady pace of creation that has been running for billions of years. The galaxy is always adding to itself, always beginning something new in some dark, cold pocket of gas, without announcement, without fanfare, in the patient dark between the stars. The universe is always in the middle of something. It does not wait for us to notice before it continues its work. Brown dwarfs are failed stars that never quite caught fire. Between the lightest stars and the heaviest planets lies a strange, dim category of object called a brown dwarf. These are bodies that formed the same way stars form, from collapsing clouds of gas, but never accumulated quite enough mass to sustain hydrogen fusion in their cores. The threshold is roughly 80 times the mass of Jupiter. Below that line, a collapsing gas cloud can glow faintly from the heat of its own contraction, and some brown dwarfs can sustain limited fusion of deuterium, a heavy form of hydrogen, for a short period. But eventually, they cool and dim. They become objects the size of large planets, but with the chemistry of stars, drifting through the galaxy in the dark, too faint to see with the naked eye, too cold to sustain the fire that would make them suns. There may be as many brown dwarfs in the galaxy as there are ordinary stars, a vast, invisible population of almost stars, resting in the dark. Something that nearly became a sun is still something remarkable. The universe holds many quiet lives that almost caught fire. Variable stars breathe in and out over regular cycles. Not all stars burn at a constant brightness. A class of stars called Cepheid variables pulsate with remarkable regularity, expanding and contracting over periods of days or weeks, brightening as they swell and dimming as they shrink. This happens because of a rhythmic cycle in the opacity of the ionized helium in their outer layers. When the layer is more opaque, it traps radiation and heats up, expanding. When it becomes more transparent, it releases the energy and contracts. The cycle repeats with extraordinary precision, and that precision is exactly what makes these stars so valuable to astronomers. In 1912, the astronomer Henrietta Swan Leavitt discovered that the period of a Cepheid's pulsation is directly related to its true luminosity. If you know how bright a star actually is, and measure how bright it appears, you can calculate exactly how far away it is. Cepheids became the first reliable rulers for measuring distances across the universe. Some things give away their secrets through the rhythm of their breathing. Even from a great distance, a pattern speaks. The largest stars in the known universe are almost too big to comprehend. The Sun is large by any ordinary standard. Roughly 1.3 million Earths could fit inside it. But some stars dwarf it to the point where comparison becomes almost meaningless. UY Scuti, a red hypergiant in our own galaxy, has a radius approximately 1,700 times that of the Sun. If placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Stephenson 218 may be even larger, with a radius close to 2,000 solar radii. These stars are so large that the speed of sound would take years to travel from their cores to their surfaces. Their outer layers are so loosely bound that they are constantly shedding enormous amounts of mass. They are, in a sense, in a permanent state of slow dissolution, enormous, dim, cool at the surface, bleeding gas into the surrounding space, burning through what little time they have, with quiet, catastrophic excess. The largest things are often the most fragile. Size, past a certain point, becomes its own kind of unraveling. Even now, as you drift, red supergiants are shedding their outer layers into the dark. The stellar wind from a red supergiant is not gentle. These stars, already swollen to hundreds of times the size of our Sun, push material outward at speeds of thousands of miles per hour, creating enormous shells of gas and dust that surround them like slow, expanding cocoons. Over tens of thousands of years, a red supergiant can shed a significant fraction of its own mass this way. Material that drifts outward, cools, condenses into dust grains, and eventually becomes part of the interstellar medium. Some of the cosmic dust floating through our galaxy right now originated in the winds of red supergiants that died billions of years ago. The dust that blocked the light in those ancient photographs of the Milky Way, the dark patches that look like gaps in the stars, much of it came from the slow exhalations of stars that no longer exist. Ancient breath still moves through the space between the stars. The past is always present in the dark, drifting slowly. Betelgeuse, one of the brightest stars in our sky, may already be close to death. Located roughly 700 light-years from Earth in the constellation Orion, Betelgeuse is a red supergiant, one of the largest stars visible to the naked eye. It is so large that if it replaced our Sun, its surface would engulf everything out to approximately the orbit of Jupiter. Betelgeuse is known to vary in brightness, dimming and brightening over irregular cycles. In late 2019 and early 2020, it underwent an unusually dramatic dimming event, fading to its lowest recorded brightness, leading many astronomers to speculate it might be approaching its final stages. It turned out to be caused by a large dust cloud shed from its surface. But the underlying reality remains. Betelgeuse is an old, massive star in the late stages of its life. When it finally explodes as a supernova, it will briefly blaze in our sky, brighter than the full moon, visible in daylight, casting faint shadows at night. Something bright in our familiar sky is quietly nearing its end. Most endings begin long before we are ready to notice them. Some supernovae are so powerful, they briefly outshine entire galaxies. A standard core collapse supernova releases an extraordinary amount of energy, roughly 10 times more energy than our Sun will emit over its entire 10 billion year lifespan. But there is a class of stellar explosion even beyond this, the hypernova, or collapsar. When a particularly massive, fast-rotating star collapses, the infalling material can form a rapidly spinning disk around the newly forming black hole, driving a pair of focused jets of energy outward from the poles of the collapse at near light speed. These jets punch through the star and produce gamma-ray bursts, the most energetic single events in the observable universe. A long gamma-ray burst can release more energy in a few seconds than the Sun will produce in its entire lifetime. They are visible across billions of light years. Tonight, somewhere in the observable universe, a star is probably ending in exactly this way. Quietly, from our vantage point, but explosively, magnificently, in the remote dark. The universe quietly performs its most extreme acts at distances that make them appear as nothing more than a faint, brief light. Quietly, the cosmos moves around you. The remnants of supernovae are not just beautiful. They are engines of new creation. When a supernova blast wave sweeps through the interstellar medium, it does not simply destroy. The shock wave compresses the gas and dust it passes through, and those regions of compression can trigger the collapse of gas clouds into new stars. Some astronomers believe that the formation of our own solar system may have been triggered, at least in part, by a nearby supernova shockwave about 4.6 billion years ago, giving the collapsing cloud that became our Sun the final nudge it needed to begin its infall. If that is true, then the death of some ancient, nameless star, a star that burned and ended billions of years before we arrived, is directly responsible for our existence. We are not just made of stardust. We are here because of a stellar death that happened before our Sun was born. We were called into being by an ending. Something had to stop for us to start. Neutron stars occasionally collide, and when they do, the universe takes notice. We touched on neutron star mergers earlier, the kilonovae that produce heavy elements. But the physics of these collisions goes even deeper. When two neutron stars spiral together and merge, they do not always form a stable object. Sometimes, the merged remnant is too massive to remain a neutron star, and it collapses further into a black hole within milliseconds of the merger. In that brief window, between the merger and the collapse, the object that exists is something for which there is no everyday analogy. It is a hypermassive neutron star, rotating hundreds of times per second, incredibly hot, emitting gravitational waves in a rapidly rising frequency called a chirp. The 2017 detection of event GW170817, when the LIGO and Virgo detectors caught the gravitational wave signal of a neutron star merger, was accompanied by a gamma-ray burst, X-ray and optical afterglows, and the spectroscopic detection of heavy elements in the kilonova. It was the most information-rich single astronomical event ever observed. Some moments hold everything: light, gravity, gold, and the distant echo of two ancient things finally finding each other. The universe holds more dead stars than living ones. Stars do not live forever, and the universe has been making them for nearly 14 billion years. When we count up the stars currently visible and burning in the Milky Way, roughly 200 billion, that number sounds enormous. But the Milky Way has been forming stars for most of its history, and most of those stars have already completed their lives. The stellar graveyard of the Milky Way contains hundreds of billions of white dwarfs, tens of billions of neutron stars, and an unknown number of stellar mass black holes. Most of these objects are invisible, white dwarfs too cool to detect at great distance, neutron stars spinning silently in the dark, black holes detectable only through their effects on nearby matter. For every star you see burning in the night sky, many more have already ended and gone dark. The sky you look at is a fraction of the history of stars that have existed in this galaxy. The living lights are only a small fraction of the story. Most of what the universe has made is quiet now and resting. White dwarfs will eventually become black dwarfs, objects that have never yet existed. The cooling of a white dwarf is an extraordinarily slow process. A white dwarf the mass of our Sun radiates heat from its surface into space and gradually decreases in temperature over billions and billions of years. Theoretical models suggest that after somewhere between 1 quadrillion and 100 quadrillion years, timescales so vast they make the current age of the universe seem like a brief introduction, a white dwarf would cool below the point of any visible glow, becoming a cold, dark, crystallized sphere of carbon and oxygen, called a black dwarf. Here is the remarkable thing. The universe is not yet old enough for a single black dwarf to exist anywhere. The oldest white dwarfs we know of have been cooling for over 13 billion years and are still warm enough to detect. The black dwarfs are coming, eventually, but the universe has not had enough time to make even one yet. The coolest, darkest ending is still patient, still waiting. The universe is not finished yet, not even close. As you rest tonight, the oldest white dwarfs in the galaxy are still slowly, barely glowing. Some of them formed from the very first generation of sun-like stars in our galaxy, objects nearly as old as the Milky Way itself, billions of years into their cooling journey. They glow a deep, dim red now. They will glow dimmer still. Astronomers can use the temperature distribution of white dwarfs in a stellar cluster to estimate the age of the cluster, because older clusters have had more time for their white dwarfs to cool, and the coolest white dwarfs mark the beginning of the cluster's stellar history. It is a kind of cosmic archaeology, reading the past through the residual warmth of ancient stellar cores. These objects have been cooling quietly since before complex life existed on Earth, before the continents were in their current positions, before the dinosaurs, before the oceans took their present forms. They are the oldest, quietest things in our stellar neighborhood. Warmth that has lasted billions of years is still warmth. Even the faintest glow is a record of something that once burned brightly. Dying stars sometimes create perfectly symmetrical structures that seem almost deliberate. The bipolar planetary nebulae, two mirrored lobes of glowing gas expanding in opposite directions from a central star, are among the most ordered structures produced by stellar death. They arise when a dying star expels material in a concentrated way along its poles, perhaps shaped by a binary companion, by magnetic fields, or by the rotation of the star itself. The result can look like a cosmic butterfly, or an hourglass, or a double bubble of gas, glowing in blues and reds. The Butterfly Nebula, also known as NGC 6302, stretches 2 light-years across and has an estimated surface temperature of around 250,000 degrees Celsius at its central star, making it one of the hottest white dwarfs known. The structure is so symmetric, so precisely shaped, that it can be hard to believe it arose from the unplanned physics of a dying star, and not from something intentional. But the universe makes order from physics alone. Order does not require intention. The universe produces symmetry simply by following its own patient rules. The iron cores of massive stars form in the final days before explosion. This is one of the more quietly extraordinary facts about stellar physics. The iron that triggers the core collapse of a massive star does not accumulate over millions of years, the way earlier elements do. Silicon burning, the fusion of silicon into iron, proceeds on a timescale of roughly a day. In a star that has been burning for millions of years, the final synthesis of its core material happens in approximately 24 hours. One day before the explosion, there is no iron core. By the end of that day, the core is full of iron, and the collapse begins. Astronomers sometimes describe it this way. A star might burn hydrogen for 10 million years, helium for 1,000,000 years, carbon for 1,000 years, oxygen for a year, and silicon for a single day. The pace accelerates, each stage shorter than the last, rushing toward an ending that was always coming, faster and faster in the final hours. Everything rushes at the end. The slow-burning life contracts, stage by stage, into a single day, and then a second, and then silence. Supernova shockwaves can travel for thousands of light years. When a massive star explodes, the material flung outward in the explosion does not simply stop after a few light years. The shockwave continues expanding into the surrounding interstellar medium, sweeping up gas as it goes, slowing gradually, losing energy over thousands of years. Some supernova remnants, the expanding shells of material from ancient explosions, are so old and so large that they are hard to recognize as remnants at all. They have expanded and thinned until they blend with the background medium of the galaxy. Astronomers estimate that most of the hot gas between the stars in the Milky Way, the interstellar medium itself, has been processed through supernova shockwaves at least once. Every atom of that diffuse gas has, at some point in the past, been heated, compressed, and flung outward by a dying star. The space between the stars is not empty or inert. It is the lingering exhale of 10 billion years of stellar death. The space between things is not nothing. It is filled with the slow exhalations of stars that burned and ended long before we arrived. Even now, as you drift, the light from a supernova that happened before the pyramids were built may be reaching Earth tonight. There are supernovae in distant galaxies, detected every year by automated telescope surveys, some in galaxies tens of millions of light years away. The ones we observe tonight happened tens of millions of years ago. But closer in, within our own galactic neighborhood, there is always the chance of a supernova, close enough to be seen with the naked eye. The last one visible without a telescope from Earth was supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 168,000 light-years away. The light from that explosion reached Earth in February 1987 and was bright enough to see with the unaided eye for several months. At its center, what remains is likely a young neutron star, still cooling, buried in expanding clouds of glowing debris, slowly drifting apart in the dark. Something that ended 168,000 years ago is still slowly unfolding. Some endings take longer than we can hold in our minds. The sound of a supernova explosion would be the loudest sound ever produced in the history of the universe, if sound could travel through space. Sound requires a medium to travel through. It is a pressure wave in matter. In the near vacuum of space, there is almost nothing for sound to travel through, and so the detonation of a star happens in silence from any practical observational standpoint. And yet there is something almost comforting in that silence. The most violent events in the cosmos, the detonation of entire stars, the collision of neutron stars, the merging of black holes, all happen without a sound reaching anywhere. We detect them in other ways, in light, in neutrinos, in gravitational waves. But audibly, the universe is vast and still, quiet in the way only something unimaginably large can be quiet. The explosions are happening out there right now, somewhere. And here, in your dark room, in the soft weight of your blankets, it is completely, gently silent. The universe performs its most extreme acts in total silence. And somehow, that silence reaches all the way to where you are resting. Neutrinos carry away most of the energy from a supernova. When a massive star's core collapses and a neutron star forms, the energy released is staggering. Roughly 300 times the total energy our sun will emit over its entire lifetime. But almost all of that energy, about 99% of it, is carried away not by light, not by the blast wave, but by neutrinos. Neutrinos are nearly massless, chargeless particles that interact almost not at all with ordinary matter. They pass through the star, through space, through planets, as though nothing were there. In the 1987 supernova in the Large Magellanic Cloud, 24 neutrinos were detected by underground neutrino detectors on Earth. A significant detection, given that the other 10 billion trillion neutrinos from that explosion passed straight through our planet without leaving any trace. You, lying still in the dark right now, are being passed through by roughly 65 billion solar neutrinos every second, streaming through every square centimeter of your body, moving on, noticing nothing. Something moves through you constantly, and you feel none of it. You are always more permeable to the universe than you know. The universe is patient, so are we. Gamma-ray bursts are the most energetic events since the Big Bang itself. In a fraction of a second to a few minutes, a gamma-ray burst can release more energy than our sun will produce in its 10 billion year lifetime. They come in two types: short bursts, lasting less than 2 seconds, which are thought to arise from neutron-star mergers, and long bursts, lasting from 2 seconds to several minutes, which arise from the collapse of rapidly rotating massive stars. Both types produce narrowly focused jets of gamma radiation, the most energetic form of light on the electromagnetic spectrum, traveling outward from the explosion at essentially the speed of light. A gamma-ray burst aimed directly at Earth from within a few thousand light-years could strip away our ozone layer and devastate life on the planet's surface. The good news is that the nearest candidates for such a burst are not pointed toward us, and long gamma-ray bursts tend to occur in smaller, lower metallicity galaxies than our own. The threat is real, but distant, quiet in probability, if not in energy. The most extreme dangers in the universe are real, but remote. The cosmos holds its breath around us, and we drift on, unharmed. Stellar mass ejections can shape entire star systems. As a massive star nears the end of its life, it does not always wait for the final core collapse to shed enormous amounts of material. Luminous blue variable stars, extremely massive, unstable stars near the theoretical maximum brightness for stars, occasionally undergo giant eruptions that eject amounts of material equivalent to several times the mass of our Sun, all at once, without completely destroying the star. The Great Eruption of Eta Carinae in 1843 was such an event. A massive star, about 7,500 light-years away, briefly became the second brightest star in the sky, without actually exploding. The material ejected in that event formed the Homunculus Nebula, two lobes of gas and dust that are still expanding outward today, moving at roughly 1.5 million miles per hour. Eta Carinae itself survived. It is still there, still massive, still unstable, still waiting. A star that came close to the edge and pulled back, carrying its enormous brightness quietly forward into the future. Something can approach the edge of ending and still continue. Not everything that nearly breaks apart is finished. Tonight, while you breathe slowly, a magnetar somewhere in the galaxy just released a burst of energy you will never hear or feel. Magnetars, those rare, extreme neutron stars with magnetic fields 1 trillion times stronger than Earth's, are not permanently quiet. They are prone to episodes of activity called soft gamma repeaters and anomalous X-ray pulsars, categories named for how we detect their outbursts. On December 27, 2004, the magnetar SGR 180620, about 50,000 light-years away, released a burst so powerful that it briefly exceeded all other sources of gamma radiation in the sky combined, and measurably ionized the upper atmosphere of Earth from that distance. If this object had been located 10 light-years away, rather than 50,000, the burst would have compared to a solar flare striking Earth at close range. From here, it registered as a brief anomaly in our instruments. From there, it was an event that reshaped the space around it in an instant, powerfully and silently, in the deep dark. The most powerful things in the universe often pass us by as signals too faint to feel. The cosmos holds its loudest events at a tender distance. Some stars die by being torn apart by another star. In binary star systems, two stars orbiting each other, the gravitational relationship between the two stars can become a slow-motion catastrophe over millions of years. If one star expands into a red giant, while the other is a compact object like a white dwarf or neutron star, Material from the giant star can begin to flow toward the compact object, forming an accretion disk of spiraling, heating gas. This process is called mass transfer, and it can proceed for millions of years, the giant slowly losing material, the compact object slowly gaining it. In some cases, the material accumulates on the surface of the compact object and ignites in periodic nova explosions. In others, the compact object grows until it crosses critical thresholds. In the most extreme cases, a neutron star can accrete enough mass to collapse further into a black hole. The giant star, whose gravity was once dominant, ends up feeding the very object that will ultimately outlast it. What you give away sometimes becomes something larger than you were. The universe finds a strange poetry in that. The oldest stars in the Milky Way are nearly as old as the universe itself. Astronomers have identified stars in the Milky Way that are estimated to be between 12 and 13.5 billion years old, in a universe that is only 13.8 billion years old. These ancient stars, found in globular clusters that orbit the outer halo of the Milky Way, formed in the very early universe, before our galaxy had fully assembled into its current spiral shape. They are made almost entirely of hydrogen and helium, with barely any of the heavier elements that later generations of stars would produce, because when they formed, those heavy elements did not yet exist in significant quantities. They have been burning quietly, steadily, at the outer edges of our galaxy, for longer than the Earth has existed by a factor of nearly 3. Some of them will still be burning long after our sun has become a white dwarf and cooled to darkness. Some things began so long ago that we can barely trace the line back to their origin. They have simply always been there, faint and patient, at the edge of the dark. Globular clusters are some of the oldest structures in the universe. A globular cluster is a tightly bound, roughly spherical collection of anywhere from tens of thousands to several million stars, all orbiting together in a compact region, typically a few dozen to a few hundred light-years across. They are ancient. Most of the Milky Way's roughly 150 known globular clusters formed in the first few billion years of the universe's history, when star formation was at its most intense. They contain many of the oldest stars known. Some are so old that astronomers have had to carefully reconcile their estimated ages with measurements of the age of the universe itself, because some initial estimates suggested the stars might be older than the universe, a problem that was eventually resolved through more precise measurements of the Hubble constant, the rate at which the universe is expanding. In the sky, globular clusters look like fuzzy stars to the naked eye, but resolve into breathtaking clouds of individual suns through a telescope. An ancient cluster, slowly circling the galaxy, carries within it stars that remember a time before Earth existed. Dark matter holds the galaxy together, invisibly and without effort. When astronomers measure how fast stars orbit the center of the Milky Way, they find something that does not add up. The stars in the outer regions of the galaxy are moving faster than they should be, given the amount of visible matter, stars, gas, dust, that we can account for. If only the visible matter existed, the outer stars would fly off into space. But they do not. Something is holding them in. That something is dark matter, a form of matter that does not emit, absorb, or reflect light of any kind. We cannot see it, cannot photograph it, cannot detect it with any telescope designed to catch electromagnetic radiation. We know it exists only because of its gravitational effects on the things we can see. Dark matter appears to form a vast, invisible halo around the Milky Way, far larger than the visible disk of the galaxy, quietly providing the gravitational scaffolding that keeps everything from drifting apart. The invisible things are often the most essential. What holds the world together rarely announces itself. We do not know what dark matter is made of. This is one of the most honest admissions in all of modern science. Astronomers and physicists have known about the need for dark matter since at least the 1970s, when Vera Rubin and her colleague Kent Ford carefully measured the rotation curves of spiral galaxies and found the same unexplained pattern over and over again. Decades of theoretical work and experimental searches have followed. The leading candidates for dark matter particles include weakly interacting massive particles, WIMPs, and axions, both of which are hypothetical particles predicted by extensions of the standard model of particle physics. So far, direct detection experiments in deep underground laboratories have not confirmed any candidate. Dark matter remains the most abundant form of matter in the universe, making up roughly 27% of the total energy content of the cosmos, and we still do not know what it is. A question that enormous, held so quietly, in the fabric of everything. Some of the largest questions have no answer yet. They simply rest at the edge of what we know, patient and unhurried. Dark energy is even more mysterious than dark matter. If dark matter is the invisible hand holding galaxies together, dark energy is the force driving everything apart. In 1998, two independent research teams studying distant Type 1a supernovae, those reliable, predictable explosions of white dwarfs, made a discovery that overturned the prevailing assumption about the fate of the universe. Instead of finding that the expansion of the universe was slowing down, as gravity would suggest, they found it was speeding up. The universe is not just expanding, it is accelerating. Something is pushing everything apart, growing stronger over cosmic time. This something is called dark energy, and it makes up roughly 68% of the total energy content of the universe. Combined with dark matter, it means that everything we can see, every star, galaxy, nebula, and planet, constitutes only about 5% of what the universe actually contains. We live in a universe almost entirely composed of things we cannot explain. We are small inhabitants of a vast mystery. That is not a frightening thought. It is, in the dark and the quiet, a deeply restful one. The expansion of the universe will eventually isolate every galaxy from every other. Project far enough into the future, trillions of years from now, and the accelerating expansion of the universe will have carried every galaxy beyond the observable horizon of every other. The Milky Way and the Andromeda Galaxy will have long since merged into a single elliptical galaxy. But beyond that merged remnant, every other galaxy will be receding so fast that its light will never reach us again. The universe will appear to contain only one galaxy, the one we inhabit. All the other hundreds of billions of galaxies will have passed beyond the horizon of visibility, carried away by the expansion of space itself. Future astronomers in that distant era, if any exist, will look out at a universe that appears to contain only their own galaxy, surrounded by a dark and apparently empty cosmos. They will have no way of knowing what we know now, that once, for a brief cosmological moment, the universe was full of visible light. What we can see now is a window that will one day close. For now, in this moment, the universe is luminous and generous with its light. Some stars explode twice. The standard story of a supernova ends with the explosion. The star destroys itself, the material disperses, and what remains is a neutron star or black hole. But in a subset of events, the star appears to explode once, brighten dramatically, and then, months or years later, explode again. These are called pulsational pair instability supernovae. In extremely massive stars, the core can reach temperatures so high that photons produce electron-positron pairs, reducing the radiation pressure supporting the core. The core contracts rapidly, triggering a partial explosion that flings off the outer layers. But the star survives, for a while. The process can repeat, each explosion shedding more mass, brightening the star dramatically, until finally, the remaining core can no longer hold itself up and collapses entirely. Astronomers have observed candidate events for this mechanism, including the remarkable IPTF 14 HLS supernova, which brightened and faded at least 5 times between 2014 and 2017, defying simple classification. Even endings can be interrupted. Some things take longer to finish than expected, and the universe is patient with them. The night sky is an archive of stellar death at every scale. Every element heavier than helium in the visible universe was forged in a star. The oxygen in the air, filling your lungs right now, was made inside massive stars that exploded billions of years ago. The carbon in your cells, in every cell of every living thing on Earth, came from the triple alpha process inside red giant stars, where 3 helium nuclei were fused into carbon at temperatures of hundreds of millions of degrees. The calcium in your bones came from supernovae. The phosphorus in your DNA came from supernovae. The sulfur, the chlorine, the potassium, all of it, assembled in the dying hearts of stars and scattered across the galaxy in their final moments. You are not simply made of stardust in a vague, poetic sense. You are made of the specific products of specific nuclear reactions that occurred inside specific categories of star at specific moments in the history of this galaxy. You are a precise, particular gift from the deaths of very specific stars. There is nothing vague or approximate about what you are made of. Quietly, the cosmos moves around you. The interstellar medium is alive with chemistry. The space between stars is not truly empty. It is threaded with atoms, molecules, ions, and dust grains in a dilute but chemically rich medium. Astronomers have detected over 200 different molecular species in interstellar space, including complex organic molecules, formaldehyde, ethanol, glycine, and amino acid precursors. These molecules form on the surfaces of dust grains, in cold, dense clouds shielded from ultraviolet radiation, through a slow chemistry that proceeds over millions of years. Some of these molecules, incorporated into the protoplanetary disks around forming stars, may be delivered to young planets through cometary impacts, seeding those worlds with the chemical building blocks of life before life has had any chance to begin. The chemistry of life may not have started on Earth, but in the cold, dark space between the stars, assembling slowly on dust grains, waiting patiently for a planet to land on. Life's ingredients were assembled in the dark, in the cold, in the space between things, long before anything alive was there to need them. The death of a star can trigger the birth of many stars. When a supernova blast wave encounters a molecular cloud, it does not simply destroy. The compression it causes can push cold gas over the threshold needed for gravitational collapse, triggering the simultaneous formation of many new stars throughout the cloud. This process is called triggered star formation, and it may explain why stars are often found in clusters, groups of stars that form together from the same cloud at roughly the same time, often triggered by the death of an earlier, larger star nearby. Our own sun may have been born this way, in a cluster of hundreds or thousands of stars, all forming together in a collapsing cloud, compressed by an ancient supernova shockwave. That cluster has long since dispersed. The sibling stars of our sun, if they exist, are now scattered across the Milky Way, unrecognizable, each one orbiting the galaxy on its own quiet path, unaware of the origin it shares with our star. Somewhere in the Milky Way, the sun has siblings it will never find. We are all more connected than we know, and more scattered. The sun will not explode as a supernova. This is worth saying clearly, because the image of the sun exploding tends to visit people late at night. Our sun does not have enough mass to end as a core collapse supernova. When it exhausts its hydrogen fuel in roughly 5 billion years, it will expand into a red giant, shed its outer layers as a planetary nebula, and leave behind a white dwarf, a quiet, cooling ember. The solar system will be changed beyond recognition. The inner planets will be consumed or scorched bare. The outer planets may survive, orbiting a dim remnant far smaller than the star they once knew. And then, over trillions of years, that white dwarf will cool and dim, slowly, without drama, without violence. The sun's ending will be a gradual fading, more like the extinguishing of a candle than the detonation of a bomb. Long, slow, gentle, and ancient. The sun will end quietly. After 10 billion years of burning, it will simply exhale, slowly, and go dim. There is something tender in that. The Milky Way and Andromeda are already falling toward each other. Right now, our galaxy and the Andromeda Galaxy, the nearest large spiral galaxy, about 2.5 million light-years away, are approaching each other at roughly 70 miles per second. In about 4.5 billion years, they will begin to collide and merge. The collision of two galaxies sounds catastrophic, but the distances between individual stars are so vast that actual stellar collisions will be extraordinarily rare. Instead, the two galaxies will interpenetrate, their stars flung into new orbits, their shapes distorted into long tidal tails of streaming light. The collision will trigger enormous bursts of new star formation as gas clouds are compressed. Over several billion years, the two spirals will merge into a single, larger elliptical galaxy, sometimes called Milkomeda. Our Sun will most likely survive, carried into a new orbit in the merged galaxy, circling a structure larger and rounder than the one we now inhabit. Everything that seems permanent is in motion. The galaxy we call home is already falling into something new, slowly and without alarm. As you rest tonight, you are traveling at remarkable speed in multiple directions simultaneously. The Earth rotates on its axis, carrying you eastward at roughly 1,000 miles per hour. The Earth orbits the Sun at about 67,000 miles per hour. The solar system moves around the center of the Milky Way at about 514,000 miles per hour, and the Milky Way itself moves through the local group of galaxies at several 100,000 miles per hour. All of this motion is continuous. It never pauses, and yet, lying still in the dark, you feel none of it. Your body, your blankets, the walls of your room, everything moves with you, at every scale, in every direction, and the net result is perfect stillness from the inside. You are one of the fastest moving things in the solar system, and you have never once felt the wind. You are still, and yet you are moving. Rest carries its own velocity, its own quiet momentum through the dark. The most distant stars ever observed are no longer where they appear. When the Hubble Space Telescope, and later the James Webb Space Telescope, observed the most distant individual stars ever detected, objects billions of light-years away, glimpsed through gravitational lensing, those stars no longer exist as they appeared. The light reaching our telescopes left those stars billions of years ago, when the universe was a fraction of its current age. In the time that light has been traveling toward us, those stars have lived and died. The universe was smaller then, hotter, more active, full of young massive stars burning through their brief lives. We are not looking at those stars as they are. We are looking at records of what they were, a photograph taken so long ago that everything in it has since changed. The universe we observe is always a museum of the past, not a window onto the present. Every light in the sky is a memory. The present state of the cosmos is something no one has ever seen, and no one ever will. Even now, as you drift, the James Webb Space Telescope is watching stars that died before Earth existed. Launched in December 2021 and reaching its operational orbit a month later, the James Webb Space Telescope is the largest and most powerful space telescope ever deployed. It observes primarily in the infrared, wavelengths of light, stretched by the expansion of the universe from the visible into the infrared during their long journey across cosmic time. Webb can observe galaxies from the first few 100 million years after the Big Bang, when the first stars were forming. In 2022 and 2023, it sent back images of galaxy clusters so distant and so ancient that the universe they inhabited looked nothing like the one we know. In those images, galaxies appear irregular, compact, colliding, chaotic. The universe in its restless youth, before it settled into the quieter, more ordered structures of today. Webb is, in a sense, a time machine pointed backward. watching the early universe assemble itself from the cold dark. We have built instruments that can see the universe as it was before the Earth existed. We are small, and yet we are astonishingly curious. Stars in different parts of the galaxy die differently because they form differently. The environment in which a star forms shapes its composition, and that composition shapes its death. Stars formed in the outer regions of the Milky Way, where gas is sparse and heavy elements are less abundant, tend to be slightly different in chemistry from stars formed in the richer, more crowded inner galaxy. The stars we observe in the small Magellanic Cloud, a small, irregular satellite galaxy of the Milky Way, are formed in a low metallicity environment similar to the early universe, and their supernovae may behave somewhat differently from those in our own galaxy. The diversity of stellar environments in the cosmos means the diversity of stellar deaths is equally vast. Different masses, different chemistries, different companion configurations, different final stages. The universe does not follow a single script. It improvises, within the rules, endlessly and without repetition, across 200 billion galaxies. No two endings are quite alike. The universe finds a new way through every time, within the same ancient laws. The surface of a neutron star may be covered in a rigid, crystalline crust. A neutron star is not a featureless sphere of uniform matter. Models suggest that it has a layered structure, a thin outer atmosphere of plasma just centimeters thick, beneath which lies a rigid crust made of heavy atomic nuclei arranged in a crystalline lattice, and deeper still, a region of free neutrons, and at the very center, possibly, something we do not yet fully understand, a phase of matter called quark-gluon plasma, or strange quark matter, in which the neutrons themselves dissolve into their constituent quarks. The crust of a neutron star is estimated to be roughly a kilometer thick and extraordinarily rigid, trillions of times harder than steel by some estimates. When the magnetic stress on this crust becomes too great, it cracks, producing the starquakes mentioned earlier. These cracks release enormous bursts of energy in milliseconds. The neutron star shivers, resets, and continues its endless, quiet spin. Even the most rigid things, under enough pressure, eventually give. And then they continue. They always continue. The universe is patient. So are we. The chemical enrichment of the universe is a story still being written. Each generation of stars born in the Milky Way is slightly richer in heavy elements than the generation before it, because the interstellar medium absorbs and retains some of the material scattered by dying stars. The first stars contained only hydrogen and helium and traces of lithium. Second-generation stars, born from the enriched remnants of the first, contain small amounts of carbon, oxygen, and other elements. Our Sun, a third-generation star, formed from material that had already been through multiple cycles of stellar birth and death, and contains a richer variety of elements that made possible the chemistry of rocky planets, oceans, and living things. Future stars, forming from the interstellar medium billions of years from now, will be even more chemically rich. The universe is, in a slow and patient sense, becoming more complex over time, not because of any design, but because dying stars keep leaving their work behind. The universe leaves something behind each time something ends. It does not waste what it has made. Stars can be ejected from their galaxies entirely. In the dense environment near the center of a galaxy, gravitational interactions between stars and the central supermassive black hole can occasionally fling a star outward at extraordinary speed. These are called hypervelocity stars, and they travel fast enough, sometimes over 1,000,000 miles per hour relative to the galaxy, to escape the gravitational pull of the Milky Way entirely. They become intergalactic stars, drifting alone through the enormous voids between galaxies, with no nearby star for companions, no galactic structure overhead, only the faint light of distant galaxy clusters visible from their surfaces. If a planet orbited such a star, an intergalactic rogue planet circling an ejected sun. Its sky would be almost completely dark, the nearest galaxy a faint smudge of distant light, the rest of the universe impossibly remote. It would be the loneliest sky imaginable, and it would be entirely silent. There are suns drifting alone between the galaxies, far from any structure, circling nothing but the dark. Even they are not truly lost. Some stars create planets in their dying. As a red giant star sheds its outer layers and forms a planetary nebula, the expelled material, rich in carbon, oxygen, and heavier elements, drifts outward and cools. In the cooling process, dust grains condense from the gas. Those dust grains are the raw material of planets. The gas and dust shells expelled by dying stars seed the interstellar medium with the ingredients of future worlds. Some of the dust in protoplanetary disks, the flat, rotating disks of gas and dust around young stars where planets form, is ancient stellar dust, pre-solar grains that formed in the winds of stars that died before our sun was born. Astronomers have found these pre-solar grains inside primitive meteorites on Earth, specks of material, older than the solar system, each one a remnant of a specific dying star, carrying in its crystal structure a record of the conditions in which it formed, billions of years before Earth existed. The ground beneath us contains grains older than the sun, each one a quiet relic of a fire that burned and ended long ago. Rogue planets are more common than stars. Planets are not always bound to stars. During the chaotic early phases of solar system formation, gravitational interactions can fling young planets out of their nascent systems entirely. These objects, called rogue planets or free-floating planets, then drift through the galaxy without any parent star, cold, dark, and alone. Recent estimates, based on gravitational microlensing surveys, suggest there may be more rogue planets in the Milky Way than there are stars, potentially trillions of them. Some may be gas giants roughly the size of Jupiter. Others may be smaller, rocky worlds, their surfaces frozen in the cold between the stars, lit only by the faint collective glow of the galaxy. Some may have kept enough internal heat from their formation to maintain liquid water beneath a thick ice shell, insulated from the cold by the very pressure of the ice above. Life, in principle, might exist on a rogue planet, far from any sun, sustained by internal warmth alone, in total darkness, without ever having seen a star. Somewhere in the dark between the stars, a world may be drifting alone, carrying warmth in its interior, asking nothing of the light. The death of stars is, ultimately, an act of generosity. When we trace the chain of stellar deaths back to its beginning and forward to where we sit tonight, the pattern that emerges is not one of loss or violence. It is one of giving. Stars are born from simple material. They spend their lives making that material more complex, and then they release it, freely, completely, into the space around them, so that it can be used again. The iron they forged, the oxygen they expelled, the carbon they synthesized, all of it is returned to the galaxy, to the next cloud, to the next star, to the next planet, to the next ocean, to the next cell, to the next living thing that lies in the dark and breathes and wonders where it came from. You are in a long line of that generosity. You did not earn the elements you are made of. They were given by stars that burned and ended long before you arrived, so that you could be here. You are the beneficiary of 10 billion years of stellar generosity. You arrived at the end of a very long gift. Even now, as you drift, the stars continue to give. The sun is giving right now, pouring energy outward in every direction, heating the planet, driving the weather, powering the photosynthesis that built the food in your body. In 5 billion years, when it expands and dies, it will give again, its outer layers forming a planetary nebula, its material scattered into space, enriching the interstellar medium for the stars that come after. Every star in the sky is in the middle of this process, receiving from the stars that came before, giving to the stars that will come after. The universe is, in this sense, an endlessly circulating gift economy, running on the energy of gravity and nuclear physics, distributing the products of stellar lives across billions of years and billions of light years of space. And you are part of it, briefly, completely, irreplaceably. You are not separate from this. You are inside it, always have been, breathing slowly in the dark. The oldest light in the universe is not from stars. It is from before stars existed. The cosmic microwave background is the afterglow of the Big Bang itself. Light released about 380,000 years after the universe began, when the cosmos cooled enough for atoms to form and photons to travel freely for the first time. That ancient light has been traveling ever since, stretched by the expansion of the universe from its original, visible, and ultraviolet wavelengths into the microwave range. It now fills the entire sky uniformly, arriving at Earth from every direction simultaneously, a faint, cold glow at about 2.7 degrees above absolute zero. When you use an old analog television, a small fraction of the static you see is caused by this ancient radiation, photons, that have been traveling since before any star existed, finally stopping in your living room, absorbed by a screen. The oldest light in the universe ends its journey in the most ordinary places. The oldest light ends its journey in quiet rooms. Something that began before stars existed finds its way, eventually, to where you are resting. We are approaching the very end of what can be said tonight. What remains is something simpler than science. The stars you can see on a clear night, on a dark hillside far from any city, with the Milky Way arching overhead like a river of faint light, number about 2,000 to the naked eye. But behind each of those points of light is a sun, and behind the faint smear of the Milky Way are hundreds of billions more, too close together to separate without a telescope. And beyond the Milky Way, in every direction, are hundreds of billions of galaxies, each containing hundreds of billions of stars. The number of stars in the observable universe is estimated at around 200 sextillion, a 2 followed by 23 zeros. And every single one of them will die, and in dying, every single one will give away everything it spent its life creating. This has been happening since the beginning. It is happening right now. 200 sextillion stars, all of them dying slowly, all of them giving. The scale is beyond comprehension, and somehow it is peaceful. The iron in your blood was forged in the heart of a dying star, not metaphorically, not approximately. Specifically, precisely, literally, every atom of iron in your hemoglobin, in the blood moving quietly through your body right now, was synthesized in the core of a massive star that exploded before our solar system was born. That iron became part of the interstellar medium. That medium collapsed into the cloud that formed our sun. That cloud flattened into a protoplanetary disk. That disk accumulated into the rocky body of early Earth. That iron was incorporated into the oceans, into minerals, into the first chemistry of life, through billions of years of geological and biological evolution, until it arrived, tonight, here, in you. You breathe, and ancient iron moves through you. You are the long patience of the universe, made briefly conscious, resting in the dark. You do not need to hold any of this. You do not need to remember the names, or the numbers, or the timescales. And all of that can drift away now, like light moving outward from a distant star, traveling further and further from its source, growing faint and gentle, and finally indistinguishable from the dark. What stays, if anything stays, is only the feeling of being very small and very held. Small, inside something vast, held inside something patient and ancient, and entirely indifferent to urgency. The universe has been doing this, burning, dying, giving, beginning again, for nearly 14 billion years. It does not hurry. It does not need to. And tonight, neither do you. Let the stars continue their slow work. Let the neutron stars spin in the dark. Let the white dwarfs cool, degree by degree, over trillions of years. Let the molecular clouds gather their slow breath toward the next generation of suns. All of it is happening, quietly, at this very moment, in every direction, at every scale. And you are in the middle of it, still and warm and small, lying in a dark room on a living planet, orbiting a middle-aged star in the outer arm of an ancient spiral galaxy. This is where you are. This is exactly where you are supposed to be. Rest now. The universe has everything else well in hand. Let your body grow heavier. Let your thoughts become slow and shapeless, the way light becomes indistinct at the edge of a nebula, not gone, just soft, just drifting, just becoming part of something larger and quieter than itself. There is nothing left to figure out tonight. There is nothing that needs your attention. The stars do not need you to watch them. The galaxy turns without your supervision. The ancient iron in your blood carries its history without any effort from you. You are, right now, exactly as complete as you need to be. The cosmos holds you the way space holds a star, without effort, without preference, without end. Sleep now, if you are ready. Or simply rest in the soft dark and let the narration carry you wherever it goes. There are no requirements here, no wrong answers, only the quiet hum of a universe going about its ancient business, and you, somewhere inside it, breathing slowly, growing still. The iron in your blood was forged in the heart of a dying star. You have always been part of this. You will always be part of this, even when the last light fades, and the last white dwarf cools, and the last sound of any kind dissolves into the final dark. The atoms that are you right now will still be here, in some form, part of some structure, part of the long, slow story the universe keeps telling itself. You are ancient. You are not separate from what is ancien. The observable universe has a horizon, and beyond it, we are permanently blind. Light travels at a fixed speed, and the universe has a finite age, roughly 13.8 billion years. This means there is a maximum distance from which light has had time to reach us. Objects beyond that distance are simply unreachable by observation, not because space ends there, but because light from those regions has not had enough time to cross the gulf between us. Cosmologists estimate the observable universe extends about 46 billion light-years in every direction, larger than the 13.8 billion light-year figure you might expect, because space itself has been expanding while the light traveled. But the full universe, the unobservable portion beyond our horizon, may be vastly larger, perhaps infinitely so. There are almost certainly stars, galaxies, and dying suns beyond the edge of what we can ever see, burning and ending in perfect, permanent silence, with no one to observe them. There are fires burning beyond the edge of what we can see. The universe does not need us to witness it in order to continue. Some stars exist in groups of 3, 4, or even 6, orbiting each other in slow, intricate patterns. We tend to imagine stars as solitary objects, each one sitting alone in the dark, surrounded by its own planets. But the majority of stars in the Milky Way are thought to exist in multiple star systems, binary pairs, triple systems, quadruple arrangements. The Alpha Centauri system, the nearest star system to our Sun, at just over 4 light-years away, contains 3 stars, 2 Sun-like stars orbiting each other closely, and Proxima Centauri, a faint red dwarf, orbiting both of them at a much greater distance. In systems with 3 or more stars, the gravitational choreography can become extraordinarily complex. Planets, if they form at all, may follow bizarre, looping orbits around shifting centers of gravity, experiencing multiple sunrises and sunsets from different suns over the course of a single day, lit by 2 or 3 simultaneous sources of light, in colors we have no name for yet. Some worlds are lit by more than one sun. They drift through more complicated light than we have ever known. The universe will eventually reach a state of maximum entropy, called the heat death. far enough into the future, so far that our current sense of time becomes meaningless. The laws of thermodynamics suggest the universe will reach a state of uniform temperature throughout. Every star will have burned out. Every black hole will have evaporated through Hawking radiation. Every proton, if current theoretical models are correct, will have decayed. What remains will be a thin, cold, perfectly uniform soup of photons and leptons, at a temperature barely above absolute zero, spread evenly across an unimaginably vast space. No gradients of temperature will remain to drive any process. No energy will flow from one place to another. No stars, no planets, no structures of any kind. The universe will be in its final, endless rest. A rest so complete that the word rest no longer carries any meaning. This is called the heat death, and it is the most patient ending imaginable. The universe itself is drifting, slowly and certainly, toward its own rest. Everything, in the end, grows still. Magnetar fields are so powerful, they could distort the shape of atoms. On Earth, the most powerful magnetic fields produced in laboratories are measured in tens of Tesla. The Earth's own magnetic field is less than 1/10,000th of a Tesla. A hospital MRI machine operates at roughly 1 to 3 Tesla. A magnetar's field reaches 10 to the power of 11 Tesla, 100 billion Tesla. At such field strengths, the electron orbitals of atoms are stretched into elongated cylinders along the field lines, dramatically changing the chemistry of any matter present. Hydrogen atoms, near a magnetar, would look nothing like the spherical hydrogen atoms in your body. They would be long, thin tubes of electron probability, stretched by the field into shapes that have no analog in any laboratory on Earth. The very concept of chemical bonding becomes something different near a magnetar. Matter in those conditions is not the matter we know. It is something quieter, stranger, and older in its implications. The rules change near the most extreme things. Some corners of the universe operate by conditions we can describe but never touch. Quietly, the cosmos moves around you. The light from the Andromeda Galaxy left before modern humans existed. The Andromeda Galaxy is the most distant object visible to the naked eye, a faint smudge of light in the constellation Andromeda, visible on dark nights as an elongated glow barely brighter than the surrounding sky. The light you see when you look at Andromeda left that galaxy approximately 2.5 million years ago, before our species had fully emerged on the African savanna, before the first stone tools of the Paleolithic, before the glaciations that shaped the current geography of the Northern Hemisphere. While that light was traveling toward you, our entire human lineage was born, lived, evolved, and arrived at this moment. The photons that reach your eyes when you look at Andromeda are older than our species. They have been traveling since before any human was alive to eventually receive them. The oldest light you can see with your own eyes left its source before the first human was born. You are the destination of a very old journey. Stellar parallax was the first method humans used to measure the distance to a star. For most of human history, the stars were simply lights, mysterious, fixed, impossibly distant, with no way to measure how far they actually were. The first successful measurement of stellar distance came in 1838, when the German astronomer Friedrich Bessel measured the parallax of a star called 61 Cygni, the tiny apparent shift in a nearby star's position against the background of more distant stars, as Earth moves from one side of its orbit to the other over 6 months. The shift was less than a third of an arcsecond, a movement so small it would be like watching a coin shift position from a distance of 2 miles. But it was enough. From that tiny wobble in the sky, Bessel calculated that 61 Cygni was roughly 10 light-years away. For the first time, a human being had measured the gap between the stars. The universe was not just large, it was measurably large. We learned to measure the immeasurable one tiny wobble at a time. The universe revealed its scale slowly to patient observers. Even now, as you drift, The Voyager 1 spacecraft is the most distant human-made object in the universe. Launched in September 1977, Voyager 1 is now more than 23 billion kilometers from Earth, well beyond the boundary of the solar wind's influence, in a region called interstellar space. It travels at roughly 38,000 miles per hour, and yet at that speed, it would take roughly 70,000 years to reach the nearest star system. The spacecraft carries a golden record, a copper disc plated with gold, containing sounds and images from Earth, music, greetings in 55 languages, the sound of rain and surf and wind, a mother's first words to her newborn child. It travels alone in the cold dark between the stars, carrying the sounds of a living planet, moving silently through a silence so vast, it makes those sounds seem all the more tender for having existed at all. We sent a golden record into the dark between the stars, not because anyone will find it, because it was the kind of thing worth doing. The sun loses mass every second, and has been doing so for 4.5 billion years. The solar wind, the constant stream of charged particles flowing outward from the sun in all directions, carries mass with it. Every second, the sun loses approximately 1 million tons of material through its solar wind alone. In addition, the sun converts about 4 million tons of mass into energy through nuclear fusion every second, via Einstein's equation relating mass and energy. Over the sun's 4.5 billion year lifetime, this mass loss adds up to a significant amount, though the sun is so large that even billions of years of this loss have barely reduced its mass by a fraction of a percent. Still, the sun is, very slowly, lighter than it was. The solar system, held in orbit by the sun's gravity, responds to this gradual lightening over geological time. The orbits of the planets drift, imperceptibly, outward. The Earth is slowly spiraling away from the sun, a few centimeters per year, patiently and without announcement. Everything is slowly, imperceptibly drifting. The Earth itself is quietly leaving, centimeter by centimeter, on a journey that takes millions of years to notice. The sun has a complex layered interior that we cannot see directly. The surface of the sun, the photosphere, is only the outermost layer we observe directly. Beneath it lies a convection zone, where hot plasma rises in enormous columns, releases its heat at the surface, cools, and sinks again in a cycle that takes weeks to complete. Below that is the radiation zone, where energy produced in the core travels outward not by convection, but by being absorbed and re-emitted by successive layers of plasma, a process so slow that a photon of light produced in the core may take between 10,000 and 100,000 years to work its way to the surface. And at the very center is the core itself, a region roughly the size of Jupiter, where temperatures reach 15 million degrees Celsius and 400 million tons of hydrogen are fused every second. The light warming your face on a sunny day began its journey in the solar core 100,000 years ago. The warmth on your skin is ancient. It left its source before modern humans walked the earth and has been traveling toward you ever since. As you rest tonight, a piece of the sun's ancient light is still locked somewhere in the radiation zone, working its way slowly outward. The random walk of a photon through the solar radiation zone is one of the more poetic journeys in astrophysics. Each photon produced by fusion is immediately absorbed by a nearby ion, which re-emits a new photon in a random direction. That photon travels a tiny distance before being absorbed again, and again, and again. Over tens of thousands of years, through countless absorptions and re-emissions, the energy gradually, randomly, stumbles outward through the dense plasma of the sun's interior, not following any path, not aiming anywhere, just diffusing outward by the mathematics of random motion. Eventually, it reaches the convection zone, is carried to the surface, and escapes as a photon of visible light or infrared radiation, finally free, finally traveling in a straight line, finally on its way across the solar system, at the speed of light. That 8-minute journey across space is the fastest part of a 100,000-year trip. Something can spend an eternity moving through the dark and then arrive in an instant. Patience, in the end, is always rewarded. Some white dwarfs are made almost entirely of crystallized carbon. They are, in the most precise sense, enormous diamonds. When a white dwarf cools sufficiently, and we are talking timescales far longer than the current age of the universe, the carbon and oxygen in its interior begin to crystallize, the way water crystallizes into ice when it cools. The resulting structure is a crystal lattice of carbon atoms under extreme pressure, essentially the same structure as a diamond, but compressed to the density of a white dwarf and spanning a sphere roughly the size of Earth. Astronomers have found evidence of crystallization already occurring in older white dwarfs, a release of latent heat during the crystallization process that slows the cooling slightly, leaving a detectable signature in the white dwarf's luminosity. In billions of years, the universe will contain countless cooling spheres of crystallized carbon, each one the remnant of a star that once burned, slowly becoming a dark diamond the size of a planet, drifting silently in the cold. In the deep future, the ruins of stars will become silent diamonds, cooling in the dark. Even endings can be quietly beautiful. The universe contains structures so large that light takes billions of years to cross them. On the very largest scales, the universe is not uniform. Galaxies are not scattered randomly, but arranged in an enormous cosmic web, a filamentary network of galaxy clusters and superclusters connected by long strands of matter, with vast empty voids between them. The largest known structure in the observable universe is called the Hercules Corona Borealis Great Wall, a concentration of galaxy clusters stretching roughly 10 billion light-years across. To cross it traveling at the speed of light, you would need 10 billion years, nearly as long as the current age of the universe. And yet, despite this enormous scale, the structure is not a solid object. It is a loose congregation of galaxy clusters, the way a coastline is a loose congregation of rocks and sand. The universe is structured but not rigid, patterned but not perfectly ordered, vast but not empty. The universe is structured at every scale, from the crystalline interior of a neutron star to a web 10 billion light-years wide. Pattern runs all the way through. The Milky Way is not where astronomers once thought it was in the universe. For most of the 20th century, astronomers believed our galaxy was part of a modest cluster of galaxies called the Local Group, the Milky Way, Andromeda, and a few dozen smaller galaxies orbiting loosely together. That picture is still accurate, but in 2014, a new mapping of galaxy velocities in our cosmic neighborhood revealed that the Local Group is itself part of a far larger structure, a supercluster of galaxies spanning over 500 million light-years, containing the mass of 100 million billion suns. This supercluster was named Laniakea, from the Hawaiian, for immeasurable heaven. We live not just in the Milky Way, or the Local Group, but in a wisp at the edge of Laniakea, a gentle curl of galaxy filaments at the far outskirts of something immense, slowly falling, along with everything nearby, toward a gravitational center called the Great Attractor, a region of concentrated mass we cannot directly observe because the plane of our own galaxy blocks our view of it. We are falling toward something we cannot see, at the edge of something we have only recently learned to name. The universe is always larger than the last map we made of it. Stars near the galactic center are older and more metal-rich than stars in the outer arms. The Milky Way has a history written in its chemistry. The oldest stars tend to be found in the central bulge and in the ancient globular clusters of the halo, formed early in the galaxy's history, when the interstellar medium was still relatively poor in heavy elements. Stars in the outer disk, including our Sun, formed later, from gas already enriched by previous generations of stellar death. And stars in the densely packed inner galaxy, where star formation has been most intense throughout the Milky Way's history, tend to be the richest in metals. carrying in their spectra the accumulated products of billions of years of stellar nucleosynthesis. In a sense, the Milky Way's chemical gradient, from metal-poor halo to metal-rich center, is a map of its own history. Reading the spectra of stars at different positions in the galaxy is like reading the growth rings of a vast cosmic tree. The galaxy carries its history in its chemistry, layer by layer, from its ancient edges to its bright and heavy center. Some dying stars leave behind no remnant at all. For the most massive stars, those greater than roughly 40 to 50 solar masses, the core collapse may be so complete that not even a neutron star survives. The entire star may fall directly into a black hole, without a visible explosion, or with only a faint, brief brightening, as some outer material is swept inward. This is called a failed supernova, or a direct collapse event. In 2009, astronomers monitoring a large red supergiant star in a galaxy about 22 million light-years away watched it simply disappear. No supernova flash, no expanding nebula, no neutron star. The star was there, and then it was not, replaced by a faint infrared glow from dust heated by the infalling material. If this interpretation is correct, some of the most massive stars in the universe end not with the grand violence of a supernova, but in complete, unhurried silence, collapsing inward in an instant, leaving nothing behind but darkness and a slight warming of the surrounding dust. Some of the largest things end without a sound. They simply stop, and the space where they were becomes dark. The hydrogen in the universe is running out, slowly and on a cosmic timescale. Every star that forms converts hydrogen into helium and heavier elements. That hydrogen, once fused, is not returned in its original form. It becomes something heavier, something that cannot fuel the next generation of stars in the same way. The universe's supply of star-forming hydrogen is finite, and it is being consumed. Cosmologists estimate that the peak of star formation in the universe occurred about 10 billion years ago, and that since then, the rate of new star formation has been declining. In our current era, the universe is forming stars at roughly 1/30th the rate it was at its peak. In the very long future, the interstellar medium will become so depleted in fresh hydrogen that new star formation will effectively cease. The last stars to form will be small, dim red dwarfs, burning slowly and faintly for trillions of years, the final embers in a universe that has exhausted its fuel. The universe is past its brightest moment. It burns more slowly now, more quietly, with less to give than it once had, and there is something restful in that. The surface temperature of a white dwarf is hotter than any star currently burning in the night sky. At first, when a white dwarf is newly formed, emerging from the hot core of a dying star, its surface temperature can reach over 100,000 degrees Celsius, far hotter than the surface of even the bluest, most massive main-sequence stars. The difference is that the white dwarf generates no new energy. All it has is what it inherited from its stellar past. So it cools from that extraordinary temperature, downward over billions of years. In its early phases, a newly formed white dwarf bathes the surrounding planetary nebula in ultraviolet radiation so intense it causes the expelled gas to glow, the same process that makes planetary nebulae visible across the galaxy. As the white dwarf cools, the nebula fades. After roughly 10,000 years, the nebula has dispersed, and the white dwarf continues its long cooling alone, dim and patient in the open dark. Something at its hottest is also at its most alone. The cooling begins the moment the burning stops. Even now, as you drift, somewhere in the galaxy, a planetary nebula is fading, its central star growing slowly dimmer. The glow of a planetary nebula is temporary by cosmic standards. The gas expelled from the dying star expands at speeds of roughly 15 to 25 miles per second, and over 10 to 30,000 years, it grows thin enough to become invisible. In the Milky Way, there are estimated to be roughly 20 to 50,000 planetary nebulae, but only about 3,000 have been catalogued, because most are either too far away, too faint, too obscured by galactic dust, or already too old and diffuse to detect. The ones we do see are a snapshot of the current population, a fraction of those present, glowing briefly against the dark. Each one is a star in transition, a moment between what something was and what it will become. Each one is a brief light in the long dark of stellar death, visible for only a fraction of a cosmic heartbeat. We see only the brief ones, the ones still bright enough to find. The rest have already faded back into the quiet. The chemical elements have distinct origins, and they are unevenly distributed across the universe. Not all heavy elements were made in the same kind of stellar event. Carbon and nitrogen are made primarily in the shells of red giant stars. And oxygen is made mainly in the cores of massive stars and scattered by supernovae. Iron is made in the cores of the most massive stars, and also in Type Ia supernova explosions of white dwarfs. Gold, platinum, and other heavy neutron capture elements are made primarily in neutron star mergers, kilonovae. Iodine, essential for life on Earth, comes mainly from supernovae. Every element in your body arrived by a different route, from a different kind of stellar death, over different timescales. The carbon in your cells came from red giants, the oxygen in your lungs from massive star cores, the iron in your blood from supernova remnants, the iodine in your thyroid from a shock wave that passed through a molecular cloud billions of years ago. You are assembled from many different stellar deaths, each contributing its specific gift. You are not the product of one star. You are the product of many, each one contributing a different piece of you across billions of years. The rotation of the Earth is slowly decreasing because of the Moon. The Moon exerts tidal forces on Earth, the familiar ocean tides, but also very slight tidal bulges in the solid rock of the Earth itself. These bulges are pulled slightly ahead of the Moon's orbital position by Earth's rotation, and the Moon's gravity tugs on them, acting as a brake on Earth's spin. The result is that Earth's rotation is gradually slowing. The day is getting longer at a rate of roughly 1.4 milliseconds per century. 4 billion years ago, a day on Earth lasted only about 6 hours. In several billion years, if the Earth still exists, a day will last much longer, possibly matching the lunar month, so that the same face of the Earth always points toward the Moon, just as the same face of the Moon always points toward us. The Moon is also slowly receding from Earth as a result, moving about 3.8 centimeters farther away each year, patiently, incrementally, in the same slow language the universe uses for everything. The Moon is leaving, the day is lengthening, everything is changing, too slowly to feel, too certainly to stop. The fate of the solar system beyond the Sun's red giant phase is a long, cold quieting. After the Sun becomes a white dwarf, the outer solar system will persist. The gas giants, stripped of their atmospheres, or perhaps intact in different forms, circling a dim, cooling stellar remnant in the dark. Jupiter and Saturn will remain, altered but present. Their moons, no longer warmed by the distant glow of a living sun, will grow colder still. Titan's thick atmosphere, which may outlast the main sequence sun for billions of years, will eventually freeze. The surfaces of the outer moons, already cold, will become colder by degrees too slow to measure without geological time. The white dwarf at the center of this quiet system will cool from white to yellow to orange to dim red over trillions of years, and what was once a solar system will become a cold, dark arrangement of frozen worlds, circling a fading ember, in a galaxy that is itself slowly winding down. The solar system will end in cold and quiet, its worlds still circling the last warmth of a dying star, patient and dark and ancient. Quietly, the cosmos moves around you. The universe has a sound, or rather, it once had one. In the first 380,000 years after the Big Bang, the universe was a dense, hot plasma, too thick for light to travel freely. In this environment, pressure waves moved through the plasma like sound waves through a gas. Enormous oscillations of density and temperature propagating outward from the initial perturbations of the Big Bang. These are called baryon acoustic oscillations, and their imprint is still visible today in the large-scale distribution of galaxies across the universe. Galaxies are slightly more likely to be found at a specific separation distance, roughly 500 million light-years, because that is how far the primordial sound wave had traveled before the universe cooled and the plasma froze into atoms, locking the wave in place. The universe rang, once, in the first moments of its existence, and the echo of that ringing is still written in the arrangement of galaxies across the sky. The universe rang once, at the beginning, and we can still read the shape of that sound in where the galaxies chose to rest. Some galaxies are actively consuming their own stars. In the centers of many galaxies, the supermassive black hole occasionally becomes active, drawing in vast quantities of gas and dust from the surrounding galaxy. As material spirals inward, it forms an accretion disk that heats to extraordinary temperatures and radiates enormous amounts of energy across the entire electromagnetic spectrum. These active galactic nuclei, including the most extreme category, quasars, can outshine the entire rest of their host galaxy, flooding the surrounding space with radiation powerful enough to strip gas from nearby star-forming regions, suppressing the formation of new stars across the entire galaxy. The central black hole, in actively feeding phases, effectively controls whether its host galaxy can continue making stars. Some galaxies appear to have been quenched, their star formation shut down, by the energetic feedback of their own central black holes, billions of years ago. The center turns on and, in turning on, dims the rest. The most energetic things in the universe sometimes prevent new things from forming. Even creation can be interrupted by what sits at the center. The James Webb Space Telescope has already changed our understanding of how early galaxies formed. Before Webb, the theoretical models of galaxy formation predicted that the very early universe should contain only small, irregular, slowly assembling proto-galaxies. The large, well-structured spirals and ellipticals we see today, taking billions of years to build up. When Webb began returning images of the universe at redshifts greater than 10, looking back to when the universe was less than 500 million years old, it found galaxies that were larger, brighter, and more structured than the models predicted. Some appeared to have already assembled stellar masses comparable to the Milky Way, in a universe only a fraction of its current age. These findings have not overturned the standard cosmological model, but they have challenged the finer details of galaxy formation theory, suggesting that stars and galaxies in the early universe assembled themselves faster than we assumed, in the dark, in the cold, with a speed the models did not anticipate. The universe moved faster in its youth than we expected. Even now, it surprises us. Even now, it is more than we thought. Rest here for a moment. There is more, always, in the dark. Some of the universe's most extreme objects were discovered entirely by accident. The first pulsar was detected in 1967 by the graduate student Jocelyn Bell Burnell, who noticed an anomalous, precisely repeating signal in her radio telescope data, a pulse arriving every 1.3 seconds with extraordinary regularity. The signal was so precise and so unexpected that it was briefly and half-seriously catalogued as LGM-1 for little green men, a joking acknowledgement that no known natural process seemed capable of producing such a clock-like signal. It was eventually understood to be a rotating neutron star, its beam of radio waves sweeping past Earth with each rotation, like a lighthouse beam. Bell Burnell's discovery opened an entirely new field of astrophysics. The Nobel Prize for the discovery was awarded to her supervisors, but not to her, a fact that has been widely noted as an oversight. The universe revealed one of its most extreme objects to a young woman, with careful eyes and a notebook, quietly. Through a radio receiver, in a field in Cambridge. Some of the largest discoveries arrive quietly, through careful attention in an unremarkable place. The universe does not announce itself. You are still, and yet you are moving. Every atom in your body is in motion. Temperature is, at its most fundamental level, the measure of how fast atoms are moving. The atoms in your body right now are vibrating, oscillating, jostling against each other at speeds that depend on their temperature, which, at body temperature, means roughly 1 to 2,000 feet per second for oxygen and nitrogen atoms in your cells. The electrons in those atoms orbit their nuclei at speeds approaching a significant fraction of the speed of light. The protons and neutrons inside the atomic nuclei are bound together by the strong nuclear force, which mediates exchanges of virtual particles in timescales so short they have no name in ordinary language. Nothing about you is still at the level of the very small. You are a storm of motion at every scale. Atoms moving, electrons orbiting, nuclear particles exchanging, and the only thing that makes you feel still is that all of this motion is perfectly balanced, perfectly contained, perfectly quiet from the outside. You are made of motion. The stillness you feel is the equilibrium of uncountable small storms, resting together in the dark. The universe has been dark for most of its history, and will be dark for most of what remains. The era of stars, the period during which the universe contains active, burning stars producing light and heat, is a brief window in the full sweep of cosmic time. Before the first stars ignited, the universe was dark for hundreds of millions of years. After the last stars burn out, trillions of years from now, the universe will be dark again, this time permanently. The stellar era, which began about 100 million years after the Big Bang, and will end somewhere between 100 trillion and 1 quadrillion years from now, occupies a tiny slice of the full timeline of the universe. We happen to exist inside that window, alive, warm, lit, and surrounded by stars. We emerged from the darkness between the first star and the last, in a moment of cosmic warmth that will not last forever, but is, right now, complete and generous and quietly everywhere. We live inside the brief warmth between two darknesses. This is not a sad thought, it is a tender one.